So we want to welcome you all for this. I'm really excited. The theme or the topic today is neural search. So Phil, our CTO from Nextiva, is going to be dropping some knowledge, but as always, we're going to, leave more than a few minutes at the end to answer any questions that you might have. We will also be posting later on a blog post because we're also going to be launching the Nextiva technology blog post. So anyway, with that, I'll leave it up to Phil for him to take over and tell us all about neural search.
All right, thanks, Ruth. And thanks everyone for joining. Really appreciate taking a little bit of time to dig into this very interesting topic. I will say at the beginning that this is really meant to be just an introduction that hopefully will stimulate your interest in digging more deeply into this exciting area of technology. And I'm gonna do my best to really just kind of bring out the basic concepts, and I'm taking a sort of a very targeted walk through the technologies to kind of bring out the basic concepts. And I'll try to point out along the way that at every point there are multiple different implementations, multiple different ways of looking at things, and I'm just going to be trying to illustrate to the big picture of how it works. I'm also going to talk about some open source technologies that are freely available that we can use. I will say that while I am going to show you I'm going to mention 3 open source projects: the Facebook similarity search project, Annoy, which is from Spotify, and Jina, which is a framework that is very powerful and convenient for pulling this stuff together. There are lots of others, and while I'm certainly very thankful to the authors of those projects for contributing them and enabling us to work with them in the community. I don't mean for this to be a commercial for any specific technology or any specific company. It's really just meant to be an introduction to neural search. Okay, so without further ado, let's just jump in. And what is neural search? At the highest level, neural search is sort of an evolution of how we think about search. And it moves away from searches that require that we have fixed rules and we zero in on keywords or other kind of regex type approaches to looking at objects under search. And instead of just relying completely on fixed rules, we make the search a little more data driven. And I'll get into a lot more detail about exactly what that means. Another important thing is that another important difference between kind of traditional search and neural search is that we use models that may have sort of been built using information that's outside of the domain of the objects being searched. And it's in a sort of intuitive sense, it's similar to what humans do when we go looking for stuff. If we say go to the library to do research, or go search, browse around the web using search tools, but then also applying our intelligence, we bring to the search more context than is actually sitting in front of us in the documents and the things that we're looking at. That's a very vague statement. Hopefully it'll become a little more clear as we move along. So again, to just kind of call out a little bit in this throat clearing part of this discussion, the difference between traditional symbolic search, and there I mean things like Lucene, Elasticsearch, the kind of standard keyword and rules-based search engines, and neural search. The real big difference is what I said before, that one is based on fixed rules, the other is more based on the data. There's no question that symbolic search is way more mature. There are really solid products, and I don't want to in any way imply that symbolic search is going away, that there's no reason to use it. There are plenty of reasons to use it. There are lots of domains where it's actually performs much better and is more suited than these emerging technologies. And we'll see that a little bit as we go along. Another difference is that that neural search, while is kind of is sort of a dual-edged sword. The fact that neural search doesn't require rules and doesn't require heuristics to be pre-programmed in. It's like a lot of things that we learn in AI, and as we apply AI to lots of different domains, that lack of explicit programming, explicit control, means that not only do you not need rules, well, it doesn't respect any rules. So it's actually very hard to get it to have completely predictable performance. So as you look at different kinds of search problems, different kinds of contexts, you really do need to think about, is neural search the right thing for you to look at? The other thing I'll point out is that it is a rapidly evolving field. It is by no means mature, and it's, in a sense, it's sort of not for the faint of heart. And that's one of the things that's cool about Jina. One of the technologies we're going to talk about later on is that it makes it a little bit more approachable. But the right kind of idea to have in your head is that currently, to get a really good neural search pipeline going does require some fairly deep technical knowledge. Okay, so what is that basic idea? I want to just kind of start with a very high level picture of what we, what is shared by most neural search pipelines. First, we start with a bunch of objects under search that could be any kinds of things. They could be text, they could be images, they could be audio, they could be video, they could be some mix of all of those things. And the first thing that we try to do is we try to take those things and get vector representations of them. So from a massive body of text, we cook it down to a vector is like just an array of numbers. You can think of it as that way. So we first try to get good vector representations of the things that we're trying to search. Then we try to find a similarity measure between those vectors that has the nice property that representations of things that are similar are close together according to some kind of metric that we put on the vector space. So we want to make it so that we want to define a similarity measure among the vectors that are the representations, so that when we compare two of them and they are close together in that metric, then the things that they correspond to are actually close together in terms of what's relevant to driving the search. And then the actual search itself really just comes down to, if you look at that kind of light blue guy in the middle there, I want to find the things that are closest to the query, which would be the one with the funny blue color. I want to find the things that are closest to it and then return the things that they represent. And that's really it. I mean, I could stop here and say that here ends, the description of neural search, and that would be fairly accurate, because that's, in a sense, most of the neural search pipelines really do work like that. And what we're now going to drill down into is, okay, what does that mean? How do you actually do it? How do you implement it in practice? Okay, first, I need to talk about representations. How do we get these vector representations that capture the things that we want and that have that nice property that representations of similar things are close together? First, the fact that we have to do representation at all is something you have to think about. A lot of what you're getting when you go from the massive object space down to the representations is a reduction in dimensionality. You're taking something like a massive video file and you're cooking it down into a vector. The raw representations really are snowflakes, so we need to do that dimension reduction. The key to doing that is what are called encoders, which are a really important part of the whole picture of neural search, which are machine learning tools that learn vector representations that bring out the salient features that we want to bring out in those snowflakes, so that the result is that the vectors that come out have that nice property that similar things are close together. So this is encoder technology is a very, very important part, and it is a part where we bring in context beyond the documents being searched. a sort of canonical example of encoder representation is what comes out of BERT in the world of text. I say it's canonical because the idea behind BERT and how it works in the world of text actually lifts to other representations as well. What BERT does is it takes a block of text and it reduces it to a vector. And what it pulls out of the block of text, the things that it uses to sort of come into its representation are the a tokenization of the input, pulling that text apart into pieces and trying to figure out sort of structurally what are the word pieces that are in the text. It looks at the positional encoding of where the individual tokens happen, and it's trained. BERT is trained to produce encodings that are optimal for solving two basic classes of problems. One problem is fill in the blanks. If I give a BERT encoder a bunch of text and I sort of gleefully pull out little pieces of it, and I apply what's called masking to pull out pieces of the input, and then I set myself the problem of fill in the missing input, then the decoders that are built on top of the BERT encoder can solve that problem well. The next problem, the other problem is next sentence prediction. So if I give a BERT engine, the BERT language model, the representation of a sentence, I can easily solve the problem of what is the next sentence in the larger corpus that that sentence was drawn from. So the right way to think of it is that the BERT encoder is trained to make the prediction of where a block of text is going easier, and it's trained on massive amounts of data. Those two examples that I just gave have the nice property that they can be trained completely self-supervised. In other words, there isn't any human that has to go and label things and say, here was the next sentence, and provide labeled sets of data. You can just feed a huge amount of text through a BERT to train BERT, and the encoder will learn the representation without any human intervention. So you can take huge amounts of data, and the right way to think about it is that as a result, BERT encoders are sort of encapsulating a knowledge of regularity in text that's drawn from a very massive corpus of text. Okay, I spent a lot of time talking about this because it's important to understand that the basic idea that what we can do in developing encoder representations is we can apply self-supervised learning to learn regularities in the input that arrive at encodings that make certain types of prediction problems easier. That's basically what BERT is. Okay, I need now to talk a little bit about vector similarity, because once we have encodings, we have to figure out what it means for things to be close together. And this will just be some really basic stuff. If you in 2 dimensions, you can view vectors as points in the plane. The most sort of naturally intuitive idea that we can that is applied to looking at vectors being similar is to look at the distance between them in the plane. So if you imagine a 2-dimensional vector as xy pair, you plot the pairs, you look at the distance between the line between them, you get what's called the Euclidean distance, or the L2 norm, that measures the distance between them. And if you want to find the nearest neighbors of a point in the plane, according to that metric, you just draw a little circle around the point, and you can see which points lie within it. Those are the ones that are close. That's a nice intuitive closeness measure. It also generalizes to higher dimensions easily. 3 dimensions, it's easy to visualize, because what happens is that little disk becomes a ball, or a sphere in 3 dimensions. Higher dimensions, you just have to use your imagination. This is not, however, the only way that you can define distance between points or similarity. Another way to look at points in the Cartesian plane is to look at vectors as little arrows that emanate from the origin and end at a point. So if I look at my 2 points A and B, I can look at the little arrows, and I can talk about their similarity or the distance between them as that angle that's in between them. And then I can define the similarity, the nearest neighbors of a point, as the set of points that are sort of that are within a little wedge formed by an angle around the point. So what you're really capturing here is that points are similar. The vectors are similar if they're pointing in the same direction, if they're pointing in a similar direction. So if they're exactly pointing in the same direction, they may be different sizes, may have different magnitude, but we view them as essentially the same vector under this kind of measure. And if they're pointing absolutely in the opposite direction, then that's as bad as it can get. That's the most dissimilar you can be. Now, this turns out actually to be a very useful measure to in NLP and in lots of neural search applications. It's sort of a lot of neural search algorithms use it as the default, and we'll talk a little bit more about why that is later. But you can just for now think of cosine similarity as measuring the degree to which the vectors are similarly oriented. So the mathematical definition is here, and I'll bring it back home with analogy to BERT encodings, which is again kind of our running example. A not terrible intuition is that BERT encodings that point in the same direction sort of indicate that the meaning is similar, and that this is very hand wavy, but it's like the admittedly hand wavy description that I gave of BERT before, that the encodings represent the encodings can be thought of as representing sort of the bidirectional, that B in BERT stands for bidirectional, the kind of bidirectional orientation of the text within the larger block that it occurs in, and it's sort of imbued with the ability to predict, to trend in the direction of where the text is going. So that's a very hand wavy description, but it turns out that it's not actually terrible. And if we say, suppose that X is a query, and we find the nearest neighbors to that query under cosine similarity with BERT encodings, you might get decent search results that way. And if you use if you use a pre-trained BERT encoder that's been trained on a very large amount of text, what's actually going on there is you are adding that additional contextual knowledge, like I described the human would bring to the problem. Again, this is we often are guilty of in AI of kind of anthropomorphizing things and oversimplifying, and this is a slight oversimplification, but the intuition I don't think is bad. I think it's a decent intuition to walk around with in terms of how in this example the encodings bring value and reduce dimensionality and help you end up with a better search. Okay, so now how do you actually make it work? I said at the beginning we could stop with that basic idea that all we really need to do is get the encodings, get a distance measure, and then find the things that are closest and done. Well, there's a big problem there in that even when you get down to 512 element vectors that you're going to get in BERT encodings, and you have a decent sized search space. When you think about it, if my algorithm is look at my query and then go compare it to every single one of the potential things in the search space, which could be very large, and then find the ones that are closest to it, that's not going to scale well. It's going to be slow. It's really sort of unwieldy. So what we need is a heuristic, some kind of way that we can make the location of nearest neighbors more efficient. This is what neural search indexers do. Face, I mentioned at the beginning, is a really nice library that basically does that. So the picture here is exactly what I've been waving my hands about. Start with the collection that you feed into an indexer. The collection in this case is images. It could be text, it could be media, it could be any kind of crazy stuff you want to search that you can encode. The Y's are the initial encodings. And then what it does is it does a very clever thing. It says, okay, I don't want to have to look at every single Y when I feed in an X, which is a query that I'm trying to match. I don't want to look at every single Y. So what I'll do is I'll extract a sort of a set of reference points, and I'll take each of my Y's that come in and I'll locate them with respect to those reference points. One not bad intuition here is it's sort of like the city block, the coarse grained quantizer, these things that basically take the large, potentially very large set of vectors and cook them down to a smaller set are called quantizers. And the coarse quantizer you could look at as locating, say, the city block, and then the fine quantizer could be the house number. And so if you have a finite set of blocks, and then within each block you have a finite set of a small finite set of actual house numbers, you can find things much faster than if you had to look at every single 1 square inch by 1 square inch coordinate in some 3-dimensional space. Okay, so Face does this, and it has a convenient way of storing an index in memory that you can then access, and you can imagine that your search is going to be a whole lot faster if you do that. There's a reference in the at the end to the paper that describes in detail exactly how this works. And Annoy is I think it stands for approximate nearest neighbors. Oh yeah, is a project that was started by Spotify, and it does the same kind of thing. It's a little bit harder to describe in simple heuristic terms. It uses separating hyperplanes and projections, but it does the same kind of thing. Reduces the number of compares that you have to do to locate a point. And it has the nice property that the index can be stored in a flat file, it can be passed around, and it supports all common distance measures. So I've only mentioned 2 in this talk, but there are many more. The 2 that I mentioned were Euclidean distance and cosine distance, and there are many more. And as I said, I'm sort of taking a slice through. Annoy has nice support for lots of different distance measures. Okay, I need to talk a little bit about the trade-offs here before we dive into a little more detail, because as we pose this problem, you can start. If I just sort of gave you this problem, said go write some code to do all this stuff, you would quickly run into this kind of basic trade-off that if you want the best quality, and quality here, I should stop for a minute and say quality, here is a mathematical concept. It's just my approximate nearest neighbor algorithm. How good is it? How good is it is mathematically defined. I can take, it's really does the approximation that my indexer does actually correspond to give me the same nearest neighbors as I would get if I exhaustively looked at every single vector. That's what quality means here. What's kind of cool is you can sample. By using sampling, you actually can evaluate the quality of these things mathematically. But the basic idea, the basic problem is that in the Face example where we looked at, we take reference points. Well, if you take many reference points, then you're going to get higher quality. If you take only like one or two, then you're going to get really bad quality. And so that kind of quality knob you can turn up and down, and that's the characteristic of all of these algorithms. You can, and as your intuition should be telling you by now, when you turn the quality knob up and down, you're going to influence speed and memory requirements. If you say add a gazillion reference points to the face model, that's going to require more memory. It's also going to slow it down because you're, in the extreme, you're going to have every point be a reference point, and you're no better than the brute force search. So the basic idea and what you run into when you actually implement these things is you have to look at these. You have to look at these dimensions. You have to decide what's important to you. What do you have? What resources do you have? The only other thing I'll mention, actually call out here, is that speed splits into two. Speed splits into an index time concern when the documents are coming in and you're indexing them, and a query time concern when you're actually executing a query. And it may make one of the two of them may be more important to you. One of the two of them may be better resource, and you need to consider that. There are algorithms that allow you to index while querying, but it's best to kind of conceptually separate the two and understand that the optimizations that you do are gonna impact one or the other differentially. And memory is memory. Another just like every other application for an application developer, the memory concerns are going to be very familiar. There's what can I store in RAM? What can I have immediately available on the GPU so that I can access it immediately? What should I use Redis? Should I use some flat file storage? All of those, just like in any other application domain, the location of the core data that's required at query time is going to determine that is going to have a big impact on the query speed and also indexing as well, and how you can distribute it. All those things come into play. Okay, so now we'll talk about how would you actually do this? What are the things that you need? What I've got here is a fairly generic picture. The field is vast, and there's lots of different ways of setting up neural search pipelines, and there's some that don't 100% fit into this picture, but most actually do. That you've got to do these things if you're trying to set up a pipeline and be able to search a whole bunch of things. First, you've got to prepare the inputs, whatever it is. The bane of existence of every AI programmer is that the real world stuff that we're working with is all this messy, funky, full of junk, and I spend all my time doing data preparation. This is the wine of every AI developer. So you don't escape that. Neural search, you've got to be able to prepare the input so that it can be brought into the pipeline. Then you have to, you've got to chunk the data. I haven't talked about chunking, and I need to just stop for 1 second and say a little bit about chunking, because it makes a big difference, and it's actually part of the overall design of the system. If you think about, say, a text search problem, and imagine that I've got a huge number of Wikipedia articles that I want to search. And my search problem is find me the Wikipedia article that has the information about the query, the thing that I'm sending in. Well, that means that the chunk that's interesting to me is the article. So what that naturally means is that those chunks are the things that I should be encoding, because that's what I'm going to look for. Those are the representations that I'm going to be working with. Imagine now that instead I want to actually look at sentences. I want to find individual sentences that have certain characteristics or match certain patterns. Well, then I'm going to have to chunk the data into sentences. The same thing applies with other media. Like, I want to find the video call where we had this terrible disagreement, or I want to find all of the 15-second chunks a video where we talked about a certain deal. Those are different problems, and they require that the data be chunked differently to set up the search. So chunking is an important part of the overall pipeline. And then encoding, we've talked at length about encoding. Indexing, we've already talked about. Then you've got to execute the queries, got to rank the results, and you get them back. This is, all of those steps are basically necessary to get this stuff to work. And then sort of as a bonus, if I'm looking for my great software framework that is going to be what I use for all of my neural search applications, what I would really like is to be able to easily plug in alternative encoders and indexers and set hyperparameters in a declarative way. And then I'd also like a deployment and execution environment. Well, it turns out that Jina really gives you pretty much all of those things. And it's a full framework for, as I said at the beginning, this is not a Jina commercial, but I'm very thankful for the developers for providing it in open source. And I do see it as something that is a very nice example and very nice motivation for all of us to think about how to pull things together and how to set up architecturally search pipelines and manage them. What Jina does is it has a structure that enables you to set up these individual things in flows, and we'll talk about that. And it provides an execution environment. It provides a sort of storage abstraction layer that enables you to manage indexes and results in a way that is declaratively configurable. And most importantly, it enables each of these kinds of things, the segmenters, the encoders, the indexers, to be pluggable. And it provides wrappers for sort of leading implementations of each of the different components. And so, for example, the face indexer, you can just plop it into a Jina flow. You have to do some configuration work to get it set up, but you now have all the power of that indexer available within a flow that you can manage. So I'm going to say a little bit about the Jina programming concepts, and just give a little example. So at the top level, Jina has the abstraction of a document, which is, you can view that as a container for searchable data which has been pre-processed. So imagine you've sort of done the pre-processing and the chunking, and now you've got the stuff that you're going to pass on to an encoder and then index and then search. The document and doc array is a nice abstraction that just enables you to represent that, feed data in, get the whole process started. Jina flows are workflows that execute it, that drive the process that we've been talking about. And they're configurable. They enable you to specify dependencies, and it's a very simple concept, but a very powerful concept, because as documents come in and they get processed, the data moves along the flow, and you get to the point where you can satisfy queries. Executors are things that decorate flows, that are actually activated by flows and that actually do work. The executors are things like crafters that pre-process source documents. Again, the unsung heroes of all AI are those who work on getting the data so it actually can come in and be processed. And the crafters provide an abstraction that enable us to get the source documents pre-processed. The segmenters do chunking. The encoders do encoding, and then the indexers index, and then the rankers and sorters do the ranking and sorting. So just to go back to the top, you have the document, which actually takes in data that isn't even yet pre-processed. And provides a container that can move down through the flow and have these various other operations performed on it. Okay, so this is a high-level picture of how it works, and a little more of the kind of runtime architecture. The flows can be configured in YAML files, so you can declaratively specify how a flow works, and also configure it in those, in the YAML file, or you could do it in code. Ps are actual execution units, so individual instances of, say, the BERT encoder will be a P that's running. Ps run inside of pods. What you're getting now is kind of a managed execution environment, and then concurrency, sequencing, and dependency are all declaratively specified in the flows themselves. So this is at a very high level the way that Jina works. Here's a really simple example. This is actually from at the end, there's a reference to the Jina GitHub. And this example is the Wikipedia sentences example that is a very simple search of exactly the kind that I described at the beginning. It uses cosine distance, it uses the BERT encoder, and it uses, in this case, it uses exhaustive sort of brute force naive search to actually get the results. So you can see in the flow specification, it's got a little bit of kind of throat clearing at the top, but then and that throat clearing, the port is interesting because under the covers, Jina really provides you with a complete execution environment that provides the inter-process communication, provides all of the glue that combines the things that are being executed in the flows. So that's a lot. When I said it provides a runtime environment, that's exactly what I mean. So here, what you've got is a specification that says, okay, I'm going to start with, my flow is going to start with an encoder, which is a transformer torch encoder that is distill BERT under the covers, Hugging Face distill BERT. This is the Hugging Face software. Again, if I'm giving commercials, I might as well mention Hugging Face and thank them profusely for all of the implementations that they make available. It's another great open source community, and they provide a variety of BERT encoders. One is distill BERT, and that's what all I have to do to get that into my flow is that one line of YAML that says, okay, use distill BERT. And the rest, all the getting the data in, getting the results out, passing it along, all that is handled by Jina. Then following that, I go to the indexer. The indexer is, as I said, the brute force indexer. I didn't put the face indexer in because there's a little more work that you have to do to get it set up and configured. And I wanted to be super, super simple here. But this actually will do exactly what I described. As just that by default, it uses cosine distance, and here it uses the distill BERT encoder. There's a little tiny bit of code to actually respond to queries from the outside if you want to have an application that kicks all this stuff off and makes it happen. And if I want to index, I basically, first of all, I load the flow. And I do that in the code saying load the flow with that flow configuration. That's precisely the YAML file that we were just looking at. I tell it where it's going to get its data from. And then I say, okay, go and index using an input generator that takes, it tells how many documents it wants to look at and what the input path is, it's going to index. And then when I want to query, it does basically the same flow, taking advantage of the fact that the indexer has already written the index to disk, and it takes a command that says search, it goes and executes the search. Okay, seem to be having some problem with, okay. So this is kind of humorous, and I did it for two reasons. One is to show what the results look like, but also to illustrate that with no fine tuning, the results can be a little bit funny. I'm not going to go into detail because I want to kind of get to the end, make sure we have enough time. But you can see in the first example, I provided the query, not theory is difficult. And the first result is, it is commonly accepted that mathematics is a difficult area of study. So you can sort of see that core intuition of pointing in the same direction is not that bad. The next one, Plato's theory of knowledge. He explains methods to help distinguish between ideas that are considered valid science and those that are considered pseudoscience. This is really interesting because, in fact, if you're familiar with Plato's theory of knowledge, the core idea there is the distinction between knowledge and true opinion, and that's sort of in there. These examples are not bad. If you implement this thing and play with it, you'll find that a lot of other examples are just completely ridiculous. Now, why are they ridiculous? They're ridiculous because I have done no fine tuning of any kind. The corpus that is being searched is randomly selected Wikipedia sentences. So this is it's using a sentence encoder model, and it's doing similarity search on the sentences. And those sentences are just, I selected 10,000 randomly selected Wikipedia sentences. So the results are going to be kind of variable and crazy. So the last concept I want to really get through is the notion of fine tuning, which is that what I just showed you is exactly what I advertised at the beginning. It's exactly just apply BERT encodings, apply cosine distance, kick out the one, find the ones that have the lowest cosine distance from the query that I typed in. In order to make things actually work better, what you typically actually want to do is you want to tune your encoder so that contextually similar documents end up with more similar encodings. For those of you familiar with NLP and solving actual NLP problems with BERT, this should be completely natural because that's what you do. That's what the fine tuning step does. So in order to fine tune, Jina provides a fine tuner that is configurable and enables you to use lots of different ways of driving the fine tuning. This one, what's shown here, uses triplet loss. Don't really have time to go into this, but basically what it comes down to is trying to force that things that we know, we provide a bunch of reference data that says, hey, these things should be close together. And I get that either via classification, via some kind of sampling that enables me to provide points that need to be, that should be close together, should be far apart. And then what you do is you define a loss function that penalizes the encoder for making things that should be close far apart or should be far apart close together. Okay, I'm going to conclude with just a little bit about multimodal search, because this is one of the things that's made possible via this whole setup. Sort of falls off the truck, and it's part of the real power of what we can do with neural search. So the queries and or search objects could be different kinds of things. You could be querying with text queries for images. They could be different languages. They could be different kinds of representations. It doesn't really matter. As long as we've got representations and we can index them together, we can drive the search. So looking for video segments using a text query, looking for text based on a video clip, searching for an item in an English language product catalog using a German audio query. All of that is possible with multimodal search, which is easily done in the general framework that we have just been talking about. So a cute example is the Jina. Again, you can get this from just go to Jina's web pages and you can download and run this, and it's really fun. What they've got is a example where they've indexed a bunch of captioned images, and now imagine that your query is a captioned image, but you have a little slider down at the bottom that says, hey, I want the text to count more, I want the image to count more, and then the results get returned weighting the caption or the image differently. And it's a toy example, but it does illustrate the power of what the kinds of things that you can actually do. The way this actually works in Jina is you set up a flow that encodes the images and the text in parallel. So you feed in the pair of documents and they get encoded on this parallel path and then join back together. And then once they're joined back together, you can power the search. It's really simple because it's almost like you just catted the two together. Now you've got one great big vector and you can search across it using exactly the same technology that we've just been talking about. All right. That I think is pretty much what I have to to present. I did want to conclude with a little commercial for Nextiva. If you don't already work at Nextiva and you're interested in working on this kind of stuff and other very interesting problems, we are hiring. So please come and talk to us. And if you do work at Nextiva, I hope that I've given you some motivation to dig more deeply into this technology. All right, and at this point, I'll just like to open it up for any questions that you have, anyone has. I'll stop sharing now.
Thank you, Phil. That was super insightful and at times, sometimes difficult, but maybe that's because I'm not really into, like doing NLP. Okay, I think we have a question, if not we just have a comment. So do we have any questions out, anybody that wants to comment on something, maybe that you want to dive deeper into some of the concepts? You can either drop the question in the chat, you can raise your hand, or you can just unmute and we can hear your voice.
Yeah, and as well, while we're waiting for people to ask anything, as I said, the presentation will be available on the inside of Nextiva on Confluence. Outside, we post it somewhere, and there are references in it to some really good references on the basically everything that I've talked about this morning. And so if you have interest, I would recommend. I like the video by the Jina person. I think is a really nice general introduction. But then there's a book chapter in there, and there's also a bunch of papers that are that really dig into the concepts. Hopefully, also this is a good commercial for some linear algebra. You can see that the linear algebra concepts are there, and that's why we do. At Nextiva, it's kind of in our core curriculum for AI NLP is really boning up on linear.
We have a question, Phil. Is there an issue at the end with kin-curse of dimensionality for a very small knowledge base? Could we further compress to a smaller space if this is the case?
I'm not sure I understand the question. Can you unmute Juan?
Yeah, Juan, do you mind sharing the question live?
Oh yeah, so basically my question is if the output vector is like in R1000, or I don't know how big it's gonna be, but if what you're doing at the end is like doing k-nearest neighbors on that, do we get any like can we do something to just check that we don't run into like bad results if we don't have enough in our knowledge base to get like good results around the query point?
Oh, I see what you're saying. Yeah, so if the document space is really small, in other words.
Yeah.
And your encoder is too big. Yeah, that definitely can be a problem. And then what you're going to have to do is you're going to have to monkey with the encoder to monkey with the encoder to make it smaller, or change your indexer so that the quality of what you're getting is better. So it's a good point that this is really designed for the setup that I described is really most applicable to large search spaces and indexing, relatively large spaces of source documents. If it's really small, then you typically want to do something else, and that something else could be changing encoders, changing distance measures, forcing very high quality in the actual search itself. All of these things. I didn't really touch at all on the detailed mechanics of how you set all the parameters and how fine tuning really works. but there's a lot to it. And that's what I meant by it's not for the faint of heart. Just if you just sort of take the defaults and set something up, you're likely going to get garbage.
Right. I guess like the main thing is like to detect if there's if your query doesn't actually match anything in your document set, then just like maybe with a threshold on the distance or something, like
yeah
distance to the smallest neighbor is large enough, you can just say, yeah, you probably don't have that in our database.
Right. And you may also want to, there's no reason, even though the what I said about the not respecting rules is true, there's no reason that you can't add heuristics on top, that you can't do additional forms of processing around the core neural search algorithm to, you know, to improve what you're returning. Also in that in the example that I gave from that little naive Wikipedia sentences thing, what was actually displayed was the similarity itself. You do get the similarity computed. So, you know, so you're right. You could a not bad approach if you want to, if you want to be able to handle somehow some elsewise way queries that you don't get good results for, is to set a threshold and not, you know, not return results that you're not confident in.
Cool, thanks.
All right,
Okay.
we have 5 more minutes. There is a quick question by Raul Martinez asking, how does this tie into or even relate to, I believe he meant AI, AR, given that these two also use a very large set of images and libraries to implement?
How does it relate to AI? Is that probably the, you know, the main, you know, first of all, there's lots of different places where we bring in, you know, the neural and neural search stands for neural networks. And there's lots of different places that neural networks can come into play in a neural search pipeline. One place is in the encoder, is in training the encoder. That's what I said at the very beginning. In the, you know, the way BERT is an encoder, it is basically, you know, the BERT encodings come from a neural network. So that's one place where it is, you know, it's straight up ML. You can also, in fine tuning, bring in neural networks to assist with the fine tuning. And then finally, there's even additional things that you can do to improve the quality of the search results that I really talk about. So that's why, you know, that it is considered an AI technology, because the AI in it is that it's not just using pre-programmed, predetermined rules to generate the search data. It's actually learning, it's actually using learned encodings and applying, you know, applying neural nets and AI algorithms to, you know, to generate the results that come out.
Thank you. And last one, only 3 minutes. How is Nextiva using this technology? And please, Phil, don't give us any confidential information.
Yeah. No forward-looking, sideways-looking, backward-looking. This is, I think it's okay for me to say that we're, you know, Nextiva has multiple search kinds of problems that are of the nature of what we just described. So we are, you know, we need to be able to search into audio, for example. We need to be able to say, find the parts of a call that talk about something or that have a certain type of situation being discussed. We have to search text in a way that when we're, you know, when we're searching when we're trying to provide search features in our communications products, we want to be able to complement traditional kind of Elasticsearch based approaches with more, I don't want to say more intelligent, but a second way of looking at deriving those results. So it's really in those areas that we are investigating the use of those products. And what I will say is this is Part of the reason we're doing this talk is it's like an internal dev invites for Nextiva. What we do at Nextiva is as we bring in technology, we first start with a very small group experimenting with it. And then we start to get ready to actually introduce it in a broader way into our products. And we want more people to learn about it. And we do exactly this. So there you go. Should be no surprise to anybody.
Great. Well, thank you so much, Phil. And thank you to all the people that, stayed throughout the tech talk. We will be bringing more of this. Maybe we'll do a neural search level 2, part 2. So that we can dive into more detail on some of the other stuff. Again, thank you, everybody. To all the people that are not part of this Nextiva, please check out all the open positions that we have. And for the people at Nextiva, thank you again for showing up and, get more of your network to come attend these types of talks. And again, Phil, thank you for doing this, and keep an eye open because this is not the last one.
Yeah, there you go. And thanks, everybody. And thanks for investing in your own development as you dive into this technology. It's fun. It's relatively easy to set up, and just try to make sure that you actually dig in and understand the concepts, because it's a little bit complicated. Thank you.